Welcome back. When we left off, this FreeCAD document had two sketches and two spreadsheets in it, and the plan was to start building the actual geometric shapes. There are some details that are, well, not necessary choices, but that I made. For instance, I have chosen this reference point which matches up with this point as our origin position for a shelf. That's not the only possible choice. We could, for instance, have chosen this point, though it doesn't exist on this shelf, it's over here. Or we could choose this point, which is the highest point where the shelf actually influences any shape. For instance, this point, which is the lowest point for the opening for the channel to the next shelf. But I ended up choosing this point. I'm going to make one more choice here, that is a choice of how wide we allow the shelf to be. If I draw a few lines here, like a horizontal line and then a line down to this, and I'll just set these two parallel. This, if I make these 2 points vertical, gives us the width at the point where the curve starts, and I think that might be a reasonable maximum width for the shelf. That way it's not actually bending multiple directions at any point. When it starts curving upwards, then it simply stops growing in width. If we do it that way, it also would make sense not to include the needless material here, so that would mean that we in fact split from here over to here. That's a minor difference. But if we do that, then the front face will also start later. It's less material, but I was thinking we might want to place a label around here. And if we do that, we only have a triangular face to do it on, which by the looks of it would be rather narrow. So I'm not entirely certain if that's a great idea. On the other hand, we might put the label just inside of this wall, not make it deep enough. But for the moment, this wall just doesn't exist. So we should start drawing the different sections. We also have particular things like this is currently just set ad hoc. I figure a reasonable height to make for the final box would be based on simply the top point of the final shelf. So let's check which constraints are actually named. Container depth. This is simply the inside depth. Container outside would be that plus 2 of the walls. We have the shelf height, which is the distance from one reference point to the next. And we also need to have something about the entrance point that defines how high this point is. A additionally, we could make some adjustments here, because by simple logic there will be exactly one of these cells that is resting on this curved surface. At the moment we have only estimated that that this cell rests on the end of the straight line. If it does so, then we see that this cell is a lot lower than the related cell here, and therefore we have more cells than we defined for each layer of shelf. So we would want to calculate the position this cell would be in order to make not this cell, but the cell behind it, around here, which actually can rest on the shelf in the same position, or at least roughly the same position. That would mean that we have two different positions for this relevant cell. One position that is the virtual position of the cell that's going straight out, and one position that is the position that a cell will actually rest in, given that there is another shelf below. Those two should not be too far apart in terms of how they constrain the cell that is to the left. But I haven't gone through that, and I think I'll save that for later. For now, let's start on actually building the shape. Do we have sufficient constraints? We want a reference constraint here that is this width. We may choose to make it different later on. I'll set it to shelf max width, negative datum constraint. That is something's bad. Everything is over. I messed up. Let's see if it's actually that broken. We may have redundant constraints somewhere, which cause the constraint system to go pretty much nuts. So let's start over with these reference lines from there to there, and we want these to be parallel, and we want it we want something to define the width we receive here. That would be that these points are vertical. It still says fully constrained sketch, so it's not unsatisfied with what we have so far. These are blue. We can make this of course. This dialog that you receive if you double click on this constraint, it changes it to an actual fixed constraint instead of a reference mode. This should be a reference mode. So we need to rename it from here. Now, 6.6 millimeters is not a wide shelf. We might want to place this at some other point, but it's a start. Let's draw some geometry. Much of this is going to be replication of what we have here. This point, I think I might redefine it as half the margin, but for starters we need to see the basic sketch of this. Well, I am unprepared as ever. We can start by drawing this bottom section. I don't need to draw all the geometry of this shelf because I'm going to define a shelf sketch that covers just this region, and I'm going to make two dependent variants of that. One that has this overhang on it, and one that does not, which is based on this bottom here. The bottom is fully supported, so it doesn't need the overhang. But let's start by defining that bottom shape. This is when I move to the part design workbench. And also I'm going to move to drawing things in the correct orientation, because all of these sketches, these calculation sketches I've done, are actually lying flat on the XY plane. But let us create a body. This shall be the bottom shelf, including the holder. So we create the sketch, we place this in the YZ plane, so if you're looking at a 3D printer, this positive Y tends to be towards the back of the printer, and Z tends to be upwards vertically. It's slightly confusing that I have different colors on these axes compared to these axes, but this red, green, blue is the traditional axis coloring, just to remind us of the order. Now, we're going to draw some real geometry here, and we're going to draw some supportive things. Remember that arc that was invisible in our front shelf? In this case, it's going to exist. We are going to draw a couple of variants here, because this time we need a wall, a real physical wall. It's going to have some thickness, and these two are centered on the last cell. So we draw a line here to place this horizontally. We have a thickness here. We can constrain it. This time we're using a real constraint. And it is from parameters, wall thickness. We want the angle between, we want to go to the bottom here. We want these to be tangent. Well, it converts it to a coincident. Well, it converts a coincident to endpoint tangency. But this means that there is no seam between this curve and this line. We want this line to be at the overhang angle. So we define it here. And we're beginning to receive a physical shape. We want a similar line heading out here towards wherever, again, tangent, that continues here, and this angle comes from, oops, that was not what I intended. This angle is going to be from the consequences. It's the shelf angle. So we're getting more constraints here. We want this radius to be the diameter over 2. We don't want this to be quite so high. I'll just constrain it vertically to the margin for now. The basic idea is still that if this cell continues rolling, then it should go up or back, it should not go out. So this may in fact be a little low. We don't want this to pass the overhang angle typically. We want this to be, oops, too many points selected. This point shall be on the floor. That's this constraint. I'm just using a lot of keyboard shortcuts. And we want the minimal thickness at the vertical point here to match the wall thickness as well. We are also going to have a bottom, so this bottom goes somewhere over there. Now you see that there are a lot of redundant constraints. That's because this bottom line is it connects to this point, which means it's already on the floor. It's set horizontal, which it, by connecting to the y-axis here, also is, that is already forced, and this says that it is on the y-axis again. So we can remove one of these constraints, it doesn't really matter which. There. We have 4 degrees of freedom. 2 of them are the placement of this section. And then there are the lengths of these 2 lines. So the next thing I want is to constrain how thick this is. I'm going to do that using some construction geometry here. So 1 point on this and onto this and vertical. No conflicts so far. Additionally, these 2 should be perpendicular. That makes this the closest point. After that, we can apply our constraint, which would be the wall thickness. This also immediately gives us our height of the shelf here, so that follows as a consequence. And we can still move this horizontally, so that we only constrain 1 degree of freedom. Now, we could add a lot of the calculating geometry again here. We are essentially drawing the same sort of sketch that we were earlier, only this time we have in mind that this shall be a physical section. But there are a few things I don't really want to include. Anyhow, we shall draw a section here. Let's set these points to be the same point. And this line, actually I don't need it at all. But we set this depth again to the wall thickness. Now we do have another parameter here, that is from the origin to this point we know how deep it is. The depth comes from the consequences container depth. And by using consequences in this case, I did not need to refer to the particular sketch in which it was calculated. So this is almost the full thing. We still have the parameter of how long this is. So we need a way to find that out. And if I look in the consequences, because that would be a consequence, this isn't actually information we have yet. So we want something parameter to set this, like say the height of the first shelf point, or yeah, that's a pretty good one. So we go into our shelf size sketch, and well, come to think of it, we have the horizontal placement of that point. We know that point is along this line, so either position would be fine. But this constraint but I'm going to make an additional reference constraint just for a little bit of clarity here. Well, unfortunately this is quite the messy sketch. I'm not sure anything becomes clear here, but I will draw it anyway. An interesting point here is that if I only have one point and select a vertical constraint, it's going to do it to the origin. So again, since this is a reference and not a true constraint, we have to rename it here. And I'll call it first shelf start height. These two constraints I want to export into the consequences sheet as well. So we head over to the consequences sheet and add the two. So this is from shelf size sketch, and first shelf start height is among the consequences. Shelf max width is one of them, and constraints first shelf start height. Let's copy that and paste it here and set the label. We are not currently in the correct workbench. We are not in the spreadsheet workbench, which makes it a little bit extra awkward, but we'll make do. Again, copy that, paste it here, and paste it as the alias. back to our bottom shelf sketch. We haven't named the sketch yet, but I think I might name the entire part when I'm that far along. So we place a point on this shelf. We constrain it vertically. This time it's a hard constraint. To consequences, first shelf start height. That actually doesn't seem to limit us all that much, because we don't know how deep in it is, but we will, because if we check our consequences again, we have well, no, we are missing that datum. Back again to our shelf size sketch. Did I forget to export this information? It's this constraint right here. I am going to name it. Shelf start depth. Sounds like a good name for it, because this is the depth from the vertical wall to where the shelf starts. And we go for the same sequence again, that we want to export this property. It's one of the named constraints. And we go into the consequences, and we shelf size sketch, shelf start depth, there it is. Copy it here and set the alias. So that's the constraint we were missing. Let's name this. This is the bottom shelf profile. And this constraint should be the only constraint that is missing here. So we place a horizontal constraint. Consequences shelf start depth. And boom, 1 degree of freedom. So there is something unconstrained according to the constraint solver. And it appears to be this, which is there because I drew this as 2 lines, and I removed the vertical line between this and this. If I had made it so that that line was construction geometry, we would have been done by now. But I did not, and we have this. I'll just remove this line because I don't need it, and set these 2 points to be the same point. Now the sketch is fully constrained. So this is our bottom shelf. We close it, and we shall pad it a bit. We pad it symmetrically, and we use a constraint that is the parameters dot length, I believe, plus the margin. And we have something that actually looks like a physical part. It is centered on the origin here. Well, not technically centered on it. The origin is placed at the front side of the container that we have not yet drawn. But this is a complete bottom. We're going to add those rolling, the curved back side. We're going to add the outside walls, and we're going to add the shelves. But this is at least our first physical part. We name this body, it's the bottom, just the bottom. It's not a complete shelf yet, but it will be after we include the curved sections. Now the curved sections are the only part of this that's actually going above this plane, so it would be okay to join up this part with the same type of shelf part. We don't need to touch the overhang as long as we just cut out the bottom, because I think that the overhang angle might end up placing the bottom of the shelf shape below the ground surface here. So let's start on making a shelf part. This is going to be a lot. It's going to be based on this shape, but we're going to need to make the overhang cut as well. And the overhang cut is slightly tricky, since we need to place it at a fairly odd angle. But we can do that with a couple of datum points. So let us move into the an appropriate orientation to see things. Not this one, not this one. Let's see only this sketch. I am going to draw the shelf outline in a new part. So we create a new body here. Can't be based on a part design feature. Well, I'm not sure what that warning was based on. I probably had something selected and it got confused, but I want to create a new body. This body will be the shelf template without the cut. A complex name, but we're going to base other parts on this part later on. Similarly, this is technically the bottom without the back curve, let's say. And this shelf template, I'm going to place it somewhat oddly here. And I use the position of the body itself to do this. We will place it in the Y position based on the depth. Consequences, shelf start depth. And in the Z position, consequences, first shelf start height. And then we start a sketch, and you see that this point is now at our reference point. This makes it easier to relate to this other sketch that contains the bottom shelf. So this is the plane I want it in, it's the YZ plane, and it's actually in the middle of that shelf, but we can adjust that later on. I placed it the bottom centered about the origin just because there is symmetry to it. Right now things look a bit funny because we don't see that the front is actually around here, but we are interested in drawing this shelf section. So we know that has a vertical line around here. We know it has a line going down at some angle here. We know there is a back wall to it, and there is the shelf section for it, and we need that arc. The arc goes from here to here. Note how the constraints fairly rapidly adjust, and this should be tangent. Yeah, I know that it's not apparently the exact correct constraint to use, but it's fine enough. We have a few other parameters. This point is in the correct place. This angle is defined. It's consequences, shelf angle. And we have much of it by now already, but this angle is also the shelf angle, if I recall correctly. And this depth and this radius are of interest. So this point should match this point. So we actually define these two to have horizontal constraints. Consequences shelf start depth, and that gives us our radius, well, eventually, because right now we don't know how high this is, and we don't know that these two are tangent. So we make them tangent, and we then don't need the coincidence. So we have 2 degrees of freedom. This, let's see, if we go back to the consequences sheet, we see that we have the shelf max width, and we have the actually the minimum size is not in here. We can see these fairly easily here as well. So we want to know how high this is and how high this is, or how deep it is. Actually, the depth is perfectly calculable right now. This is the consequences container depth minus the consequences shelf start depth. Because this start depth is also how far this point is from the front wall. So we are down to fewer constraints. If we look in the task, we see 1 degree of freedom. This is that degree of freedom. So in order to create the proper constraints here, we shall draw from this point to this point we shall set the angle to the overhang angle, and this point shall have its width set to the minimum shelf width. There, we have a fully constrained shelf part. I'm going to pad it to give it a physical form, and this should be the shelf max width. This obviously is not the position it should be in. It's going to be more clear if we re-enable not just the bottom shelf profile, but the actual bottom shelf physical shape. So this needs to be offset, and the particular offset is in the X direction, and we want to move it over to this wall. So we adjust this as well to the parameters dot length plus margin. Again, this is a formula that is repeated in several places, so we might want to make a note of it and collect all those like in the consequences sheet and divide by 2 and offset it negatively. There, it is now correctly placed, and we see some graphical artifacts here because this is an overlapping surface. We also see that it pokes out below, and finally this is completely horizontal, so the overhang angle is not included in this shape, but it's largely there. Also, we could have made it much wider back here if we wanted to. We limited the width by this point, so it would be around here probably. Next, I'll want to mirror this because we're not satisfied with having it supported on only one side. This we do in the part workbench. At least I think we do it in the part workbench. So we have this part and we want to mirror it. That looks like mirroring. So we mirror the shelf template, and the plane we choose to mirror it in is in the ZY plane. Or YZ, doesn't matter. And we have no offset because we centered this earlier. There. We now have the mirrored version of the shelf, and we can add, we now have 2 distinct cuts to make from the shelf. For the bottom shelf, the cut needs to be at the bottom, and for the array of further shelves, the cuts need to be in the overhang section of it. Now we could include the overhang cut in the bottom shelf as well, but if we choose to make the shelf wider up here, then that will create an awkward corner in here. Not that it wouldn't work, it just would look strange. for the moment, I think we can remove that now. Let's start with adjusting the bottom. So these two clearly need to go together. We just select both of them, and in the part workbench we perform a union, which is called a fusion here. And if we set refine to true, then these surfaces are merged and it's no longer, well, they should be. The original template is, oh, well, now that was an effect I wasn't thinking of. I wanted the mirror as well. Let's do that mirror again. It's not in, it's in YZ. There. This mirror part is actually a completely distinct part. Both of them are not in the origin here. And that's going to matter at some point fairly soon. But for the moment, I think I want to join these two into one part. And this part is the one I'm going to duplicate for the shelves and so on. Although I might not want... I'm not thinking straight, as usual. The tricky part is the overhang cut, so we'll look into that later. For the moment, we could actually make a fusion of all of these for the bottom shelf, and we need to make that cut. So in this case, we create a cube. We set this cube the cube needs to be okay, which axis is which on this cube? I don't know. Placement. We want it over here, so our X placement is parameters length and parameters margin. And this is confusing. It says there is a unit mismatch. Parameters length is in millimeters, and so is margin. So why am I having trouble editing this placement? In fact, it should be based on the same as this. So that's also a placement. It should be perfectly fine to enter it like that. Good. And now the cube is in the right position, and we want to adjust its width, I believe. Nope. No, that's the value I want, but it should apparently be set in the length field. There we go. And we want to go all the way back, and that's apparently this field. That's container depth. And the height is consequences shelf height is a nice one. And we do simply adjust its position like that. This box, well, it's apparently slightly longer than I need. That's not actually correct, it's misplaced. It's not as wide as I need it to be. And that could be this. Now it's deeper, which means I've got those mixed up. The parameter I have set at width is what we should have for length, and vice versa. So let's readjust them again. This was from the consequences. There. Now this box represents space that is below and needs to be cut away. So I can select this fusion and this cube and perform a subtraction or a cut. This cut is our bottom, excluding the actual walls of the casing. And it's not set to refine, but I believe that we can get rid of these odd edges if we set refine to true. There you go. You may have noticed that I did a lot of shape cuts and so on, where the shapes are perfectly coincident. That is possible for these solid boundary shapes that are completely algebraically defined and not defined by having floating point numbers that may or may not have matching precision. I'm not sure. Actually, I'm not sure where the boundaries go precisely. In some systems, you may need to make sure that, for instance, the box that you use to cut the bottom parts here would be a little bit deeper, things like that. But for now, this shape is doing fairly well. Next step, we want to define the shelf with the overhang cut. And we're going to use this shelf template without overhang cut to do it. So we're going to make not exactly a clone of it, we're going to mirror it again. And this time we're going to mirror it along the XZ plane, or across the XZ plane. and we're going to apply a depth in the y-axis. This depth, unfortunately, it's this is one of those points where we had difficulty entering a formula, so we might want to make a workaround. In this case, I am going to create a datum plane, I believe, but I may be mistaken, and that could be a tool that's not easily available. Here, a datum plane. I want to create a plane in that is XZ. So we're going to look at we will use this part for this task because it appears that the datum plane requires an active body, and we shall attach it to the objects XZ. Need to display that and not. Sorry, I'm going to have to take a pause.